Hello, very good afternoon. Myself Sunil Kumar ojha, Assistant Professor in Mechanical Engineering Department, IIMT College of Engineering, Greater Noida. Today I am going to deliver a video lecture on wind energy and its utilization. So, as we know, what is wind? So, wind is nothing but air is constantly moving around the earth, and this moving air is called wind. Winds are created when there are differences in air pressure from one area to another area. In areas of high pressure, sinking air and air at the ground level is spread out and moving away from the high pressure. So this way the due to pressure difference created that air particles will move from high pressure to low pressure. That flow of air will takes place. Where this pressure difference created from the energy source is solar radiation. Solar radiations that will create due to differently absorb the earth surface, convective heating and cooling, that temperature difference that will create pressure difference, and the air will having the motion. So this is the something we know the wind. There are different types of wind. Uh, Planetary circulation of wind. There is equator having maximum solar radiation, and when we have to go to the poles, there is a high difference, and there is a sun intensity is low on the poles, so there is that creates pressure difference, and that will there is a planetary circulation of wind. Same as a geostrophic winds, there is thermal winds, gradient winds, katabatic winds, that is called topographic winds, bora winds, chinook, downslope wind storm, sea breeze, land breeze winds, convective storms, hurricanes, typhoons, tornadoes, gust, dust devils, nocturnal jets, atmospheric waves. So these are the different types of wind we know. Uh, so we have to find out the ways to utilize the wind. So why we, as we know, the wind has power. So wind energy utilization is not exactly the new idea. We have from ancient times we are using wind power to utilize for our purpose. Like from ancient time there is sailing ships. We have to sail the ships through the wind, as we know. We can see in the sea areas from ancient time, when there is no far, we have to utilize the wind source to sail the ship. There is a windmills. We have to use the windmills. There is a wind pump. We have to use the wind pump to extract the groundwater into the for irrigation purposes. There is a grain mills. We have to utilize the wind power for grinding the grains. So there is grain that is used by the we have to use the wind power to grain the grains. So from ancient times we are harvesting the wind power. Nowadays we have to utilize the wind power from other purposes for most of the generating the electricity. So why we are focusing on wind power? So as the advantage of wind power is it has it is the renewable source of energy. Wind power is a renewable source of energy. It will not exhaust. Okay. That's why we have to focus on wind power. It is cost effective. So as we have utilizing most of the wind energy, the cost is go lower run, and it comes to the non-renewable source of energy or fossil fuel near about that. So wind power is cost effective. That's why we have to focus. Wind energy creates jobs. Wind enables us to industry growth and competitiveness. Wind is a domestic source of energy. That's why we can utilize that. It is sustainable. The wind power, utilizing the wind power itself is a sustainable source of power. Wind turbines can build on the existing farms or ranches. We can build the wind turbines to harness, to utilize the wind energy. And wind power is a clean source of energy, or say non-polluting source of energy. That's why these are the some advantages of utilizing the wind power. So how we have to calculate the wind power? So fundamental equation, when we have to mathematically formulate how much there is a power. So we can formulate the fundamental equation of wind power. As we know, wind power depends upon how much amount of air or volume of air, speed of air, what is the velocity of air, that, and mass of the air. So we have to calculate in terms of density. Flowing through the area of interest, that is flux. So we can calculate the, as we know, kinetic energy is half mv square, where m is the mass and v is the velocity. So putting these values in this kinetic energy equation, we can and m is equal to dm by dt, mass flux, power, kinetic energy per unit time. So we can calculate the power half and v square, mv square. So into fluid mechanics, we have the mass flow rate, density into volume flux. So dm by dt is equal to rho av. So this way we can formulate the wind power. So wind having the power P is equal to half rho a v cube. So where power is the proportional to cube of velocity, power is proportional to air density, and power is proportional to rotor swept area, where we can, that's so simply we can say area, swept area. That is, if we have to, in terms of swept area, we have to put the value pi r square or pi by 4 d square. So we can calculate, harness the how much power we can find out. So this is P is equal to, from this equation we can calculate the wind power. P is equal to half rho a v cube. Next, there is a how much efficiency extracting the wind power. So we can calculate efficiency is nothing but output upon input. So output input is nothing but wind power. As we know, wind power is this half rho a v cube, and output is how much we can extract. That is called efficiency. So power efficiency Cp is the nothing but ratio of extracting the wind. So when for harnessing the wind energy, we have to put the install some mechanism that is called wind turbine. So through the wind turbine, we can generate the utilize the power. So that is the power efficiency of wind turbine is nothing but power coefficient Cp and ratio of power extracted by the wind turbine to total contain the wind resource. So Cp, or say power coefficient Cp is equal to Pt upon Pw. Power of the wind turbine Pt divided by power of wind. So power output we can calculate Pt half rho a v cube into Cp. So there is Cp is nothing but bed limit is the maximum possible amount of power extraction from the wind. So bed limit is that limit. So when we have to formulate, put these values on the equation, we will find that Cp is equal to 16 upon 27, or say something 59% efficiency of, it is the maximum efficiency that we can harness through the formulation. That is called bed limits. So up to 59% efficiency we can is the best efficiency a conventional wind turbine can do extracting power from the wind. So bed limit is nothing but it is a flow of air over the blades and through the rotor area that makes the wind turbine function. The wind turbine extract energy by slowing down the wind. Theoretically, maximum bed limit is nothing but theoretical maximum amount of energy in the wind that can be collected by the wind turbine rotor is approximately 59% or 59.3%. This value is known as bed limit. If the blades are 100% efficient, a wind turbine would not work. So, if we have to extract 100% energy from the wind, means that flow of wind we have to block down. So that's why it is not possible to harness 100% energy from the wind. If we have to do that, the wind turbine would not able to work because the air having up giving up all its energy and would entirely stop that. So that mechanism, that function will not work. So we have to not able to extract 100% energy. So that limit is best limit, that is 59%. In practice, the collection efficiency of rotor is not as high as 59%. So in the practical work, the maximum theoretical efficiency is 59%. And in the reality, practical work, that efficiency are much below than the 59%. More typical efficiency is 30.5 to in practically the efficient energy or practical energy efficiency is around 35 to 45%. A complete wind energy system include rotor, transmission generator, and other devices which all have less or perfect efficiencies. Will deliver between 10 to 30% of original efficiency available in the wind. So we have to find out there are two forces in the wind turbines. As we know, we have to utilize the wind turbines. So there are two forces act on it. There is a lift force and there is a drag force. So in the moving stream, when we have to put any object, there are two forces acting on it. One is lift force and other is drag force. Drag force is horizontal to the moving stream velocity. Say simple, if we that is wind. So when we have to put any object on the moving wind stream, so there is horizontal force acting on the along the moving stream of it, that is called drag force, and there is a uplift vertical force acting on that object, that is called lift. So we have to make the wind turbine blades. We have to give that some aerodynamic shape, like in aeroplane. There is a aeroplane. So there is a lift and drag force acting on aeroplane profile, that wings. So same as we have to make the blade this shape, airfoil shape on the blades. So there is a drag and lift force acting on it. So we can see in the diagram picture, this there is a this is the wind turbine, and there is a wind flow that blades is the wind is passing through the blades, and that in the blade this will act as a object. This blade is act as an object in between the flowing stream of it. So this will there is a two forces acting on the blade. One is the drag force and another is lift force. So these two forces are very important for running the turbine blades. We will see in the later. So what is wind turbine? For harnessing the wind energy, we have to use wind turbines. The wind energy is created when the atmosphere is heated evenly by the sun, and some of patches of the air becomes warmer than the other. These warm patches of air rise and air rush into replace them that the wind blows. The wind turbine extract energy from the moving air by slowing down the wind down and transferring this energy into the spinning shaft, which usually turns the generator to produce the electricity. So wind and turbine is nothing but we have to extract the energy from the wind and run down this transferring the wind energy through the mechanical motion of the shaft, and that runs the generator to produce the electricity. The power is the wind that is available for harvesting depends upon both uh, wind speed and the area that swept by the turbine blades. So the power is nothing but depends upon the wind speed, as in the previous equation, half rho a v cube. So power depends upon the velocity of the wind, and area, how much area we have to swept by the turbine blades. So that depends on these two factors. So wind turbines, there are two types of wind turbines are possible to harness the wind energy. That is, two types is, one is the horizontal axis and another is vertical axis. So wind turbines are two types: horizontal axis wind turbine and vertical axis wind turbine. So what is horizontal axis wind turbines? On the flowing stream of the wind, the axis of rotation of turbine blade is parallel to the flowing velocity of the wind or parallel to the ground. That is called horizontal axis wind turbine. You can see in the right of the diagram. Right side diagram is horizontal axis wind turbine. And what is vertical axis wind turbine? In the vertical axis wind turbine, the axis of rotation of turbine is vertical to the flowing velocity of the wind. Vertical to the flowing velocity of the wind. That is called vertical axis wind turbine. So there are two possible based on the axis of rotation. These two types: horizontal axis wind turbine and vertical axis wind turbine. In horizontal axis turbine, it is possible to catch more wind, and so the power output can be higher than the vertical axis. So in comparison, the horizontal axis wind turbine mostly used because we can harness more power output. But in horizontal axis design, the tower is higher and more blade design parameters have to be defined. In vertical axis turbine, no yaw system is required and there is no cycle load on the blade. Thus, it is easier to design. Maintenance is easier in the vertical axis turbine, whereas horizontal axis turbines offers better performance. So these are the two possible based on the axis of rotation. So we have to see in the next the types of wind turbines. So there is a windmill. If the mechanical energy is used directly by the machinery, such as pumps, grinding stones, and machine usually called windmills. So from the ancient times, we are using this type of windmills. Wind turbines. What is wind turbines? So if the mechanical energy is converted into electricity, uh, means wind energy converted into mechanical energy, and that mechanical energy converted into electricity, the machine is called wind generator. The types of wind turbines, so as we know, there is a two possible based on the axis of rotation: vertical axis wind turbine and horizontal axis wind turbine. So vertical axis wind turbines, although vertical axis wind turbines have existed for centuries, they are not as common as their horizontal counterparts. The main reason is that they do not take advantage of higher wind speed at the higher elevation above the ground level as the horizontal axis turbine. An entry early wind turbine, the from the as we know, the vertical axis wind turbine used from the ancient times. The Persian, that is called Persian windmills, was used around the 1000 BC to turn the grinding stones. This is oldest known windmill design. The machine works on the blocking the wind, blowing on half of its sail. The sail exposed to the wind are pushed downwind due to drag, causing the windmill to rotate. Anemometer. Anemometer is nothing but it is the instrument for measuring the speed of air flow. So in the roofs, we can see when we require to measure the speed of the airflow. A cup type of anemometer is drag type vertical axis wind turbine. So this is the small anemometer we have to use for measuring the speed of the airflow. Another is Savinus wind turbine. The there is that is if we look from the vertical, uh, from the top, it is look like something S shape. So Savinus turbine is S shape if viewed from the above. It is called drag type vertical axis wind turbine. Turns is relatively slow, but yields high torque. So it is rotation is slow, something slow, but turns it has high torque. It is used for grinding the grains, pumping the water, and mainly other tasks. But it is it's slow due to its slow rotational speed, takes unsuitable for generating the electricity on large scale. So this purpose is used for irrigation or grinding purpose. This Savinus wind turbine. Next is flapping panel wind turbine. You can see in the diagram there is flaps. The illustration so the wind coming from the one direction, but the wind can actually come from any direction, and the wind turbine will work at the same way. Next is another is vertical axis wind turbine, that is called Darius wind turbine. So the Darius wind turbine is most famous vertical axis wind turbine, is characterized by the C-shaped rotor blade. So there is a C-shaped rotor blade which gives the egg beater appearance. It is normally built with 2 or 3 blades. So this is Darius types wind turbine. The Darius turbine is not self-starting. It needs to start turbine before the wind mill begins to rotate it. So it is not self-starting. We have to rotate the first wind turbine before the wind will begin to rotate that mechanism. Gyro mills the wind turbine. The gyro mill is typically powered by 2 or 3 vertical aerofoils attached to the central mast by the horizontal support. Next is so this is all these are the whether it is we can say Savinus wind turbine or Darius type. These two are vertical axis wind turbine. It has high rotational speed but low torque. So these are not positioned on the very high on the height. It is near about the ground level, placed on the ground level. Next is very important is horizontal axis wind turbines. So horizontal axis wind turbines are most common wind turbines designs in addition to being parallel to the ground. The axis of blade rotation is parallel to the wind flow. That is called horizontal axis wind turbines. There are, it has 2 types, up wind turbines and down wind turbines. Next main components of horizontal axis is rotor, generator. You can see in this rotor there is a that converts the wind power into rotational mechanical power. There is a generator that converts the rotational and mechanical power into electrical power. There is a gearbox. The wind turbines rotate typically 20 rpm to 400 rpm. Generators typically rotates at 1200 to 1800 rpm. There is a rotor. The rotor portion of wind turbine collects the energy from winds is called rotor. The rotor usually consists of 2 or more wooden, fiberglass, or metal blades. Next, all the main components. This is some actual diagram. This has rotor, pitch. You can see in the diagram there is a rotor in the front side, pitch drive, nacelle. The whole mechanism back to the rotor is called nacelle, where all the mechanism is placed above it. Brakes, there is a low speed shaft, gearbox is attached on that. There is high speed shaft that is attached to the generator, and there is generator units, heat exchanger unit to keep the generator cool down, and there is a controller. A computer system runs the self-diagnosed test, start and stop of the turbines, and make the adjustment as wind speed is vary. The direction as there is a direct change in direction of wind, according to that, the controller will adjust that accordingly. There is anemometer to measure the speed of the what is the speed of the wind, and wind vanes, and yaw control drive that keeps the whole tower mechanism to adjust the according to facing of the wind. And there is a tower. So that is the something components of horizontal axis wind turbine. So rotor blades variables, the rotor blades variables are blade length, how much number of blade pitch, and blade shape profile, what should be profile, and weight, blade of the material, weight. So for our class, we have to control over the three parameters of what should be blade profile, what should have the angle of attack, and how many blades we have to use. So as we know, there are two types of principles we have to use. There is design, drag design. So in the vertical axis wind turbine, we have to use drag, mostly drag, for utilizing that drag force, for utilizing the converting wind energy into our another purpose, harnessing the. And so these are the vertical axis wind turbines based on the drag principle. So in the vertical axis wind turbines, we have to utilize the drag force mostly to convert wind energy into useful purpose. In the lift design, mostly the vertical axis wind turbine uses the lift design principle, although there is a drag force, but mostly we have to utilize both lift and drag force to harness the convert into electricity. So this is the some profile of the blade that is called airfoil blades. So there are chord line, and there is an angle of attack. So angle of attack is nothing but chord line and the relative wind speed. The angle between that is called angle of attack. And there is there is two component of forces. Vertical force is lift force, and horizontal force is called drag force. So, and there is a center of pressure. So this is the something mechanism of the airfoil or wind turbine blade. So wind turbine blade design, so angle of attack, we have to adjust the angle of attack is between the chord line and direction, flight direction, or say something wind velocity, and that wind direction of velocity, that is called angle of attack. The angle of attack we have to adjust ranges from 1 to 15 degree. So the propeller efficiency typically numbers can be ranges from 1 to 15 degree. Angle of attack. So as if we have to increase more angle of attack, that will stall the wind turbine blade, mean it will not harness the amount. So that optimum level is 1 to 15 degree. Next is how much number of blades we have to put in the horizontal axis wind turbines, whether it should be one blade, two blade, three blade, or multi-blade system, four blade, another. So determination of number of blades involves design consideration, aerodynamic efficiency, component cost, system reliability, and aesthetics. The aerodynamic efficiency increases with the number of blades, but diminishing return. One or two blades increases yields 6% increase in efficiency, whereas increasing the number count 2 or 3 yields 3% only, an addition of 3% in efficiency. Further, increasing the blade count yields minimum improvement in aerodynamic efficiency. Generally, fewer number of blades we have to use. The lower the material and manufacturing cost, higher rotational speed reduces the torque in the drivetrain, resulting in the real wash cost. Even so, what should be even or odd number of blades? So a rotor will with an even number of blades means 2, 4, or 6 combination problem causes the stability problem in the wind turbine. The reason is that's why we the very moment when upstream blade bends backwards causes the maximum power from the wind. So we have to use uneven number of blades. Mostly 3 number of blades is more suitable for that stability. So the blade linear velocity we can calculate, as we know, V is equal to R omega. R is the radius of blade and omega is the rotational speed. So wind turbine design shape. So as we know, the aerodynamic shape is suitable, and there is a so we can see there is that aerodynamic shape of the wind turbine blades. There is there is a blade twist. So we have to twist the blade according to So rotor blades of wind are always twisted. We have to twist the some degree. Uh, the blades are twisted from the angle, some angle. So seen from the rotor blade, the wind will be coming from the much steeper angle with the direction of landscape. So as you move towards the root of the blade and the center of the rotor blade will stop giving lift. And it will, if the blade is hit at angle of attack, which is too steep, therefore rotor blade has twisted. So we can say these are the swept area. So 0 to 10 miles, 10 to 25 miles. So typical wind turbine blades are working on 20 to 25 miles per hour. So next year we have to go for see these are the some technical specification of 10 megawatt wind turbine. So number of blades 3, airfoil size. Okay. So 10 and power generation in financial year around this percentage is showing to 4.6%, around 4.5% is contributed to by the wind. India cumulative wind is around by the wind turbine is around 40 gigawatt. So last year it is these are the states which are producing. So Tamil Nadu is the major state that is producing total wind power out of which 25%, and Gujarat is 22%, and rest of these showing in this diagram. And wind power in India is the currently we are generating 40 gigawatt power from the wind, and it is the fourth largest country in terms of wind. These are the states where we have to produce wind power. These are the sites, plants, and in the right side